Hello everyone, this is the second part of the lecture number 6. In the first part of lecture number 6 we have discussed about the limit point of a sequence, and actually it is not necessary that every sequence has a limit point. There are many sequences which has no limit point. For example, a sequence n terms are 1, 2, 3, 4 and so on. This sequence has no limit point. Similarly, you can take 2n square plus 1 and n cube have no limit points. Actually, in this lecture we find the condition that a given sequence has at least one limit point. Then if a sequence is bounded, then this sequence always has a limit point, at least one limit point if sequence is bounded. Okay, and this result is known as Bolzano Weierstrass theorem. According to this theorem, a bounded sequence has at least one limit point, has at least one limit point. If the sequence is bounded, then it means that the sequence has at least one limit point. Okay, now we will prove this theorem. This theorem is very important. Suppose that an be a bounded sequence. Okay, then we have to show that an has at least one limit point. Okay, sequence is bounded, and we know that if a sequence is bounded, note a point, if a or we can write a sequence is bounded if and only if its range is bounded. Okay, suppose that we have a sequence which is bounded, then this implies that the range of that sequence is bounded, and converse means if range is bounded, then this implies that the given sequence is bounded. Here we suppose that actually in this theorem we have a bounded sequence. Okay, and we suppose that a and b a bounded sequence. Okay, so why this result? Therefore the range actually is a set of distinct member of the sequence. Sequence is bounded, then range of sequence an is also bounded. Range of this sequence S is also bounded. Here an is a sequence and S is a collections of all distinct element, okay, of the sequence. So we have a bounded sequence and we suppose that its range is S. So by the result that if a sequence is bounded, then its range is also bounded. S is bounded. There are two possibilities. There are two cases. S is finite, and second case S is infinite. Okay, S is range. Range means a set of the given sequence. Clear? So there are two possibility. This possibility actually is true for any set. Set is either finite or infinite. Okay. Now we take the first case. S is finite. Clear? In this case, we show that the given sequence has a limit point. If range of the sequence is finite, this implies that there must exist at least one element which repeated infinitely times. Okay, since range S of an is finite, therefore there must exist at least one member of the sequence an, one member of the sequence, and suppose this is L. There exists one member of sequence an which repeated infinitely times. That is an is equal to L for infinitely values of n. Okay, because the L is repeated infinitely times. Okay, because the range is finite. Clear? This implies that an goes to L minus epsilon, L plus epsilon, because this is the neighborhood of L, and neighborhood of L means this neighborhood is also contain L, and here L repeated infinitely times. So therefore that repeated elements also belongs to this neighborhood for infinitely many values of n. Okay, here we take a case first. Suppose S is range S is finite, so there must exist at least one element of the range of the range sorry of the there must exist at least one element of the sequence an which repeated infinitely times because range is finite. Clear? We take that repeated element is L, so it is clear that an is equal to L for infinitely values of n. Okay, and this is the neighborhood also contained for infinitely values of n. Now this is true for every epsilon positive. Clear? This implies that every neighborhood of L contains infinitely many member of given sequence an. This implies that L is the limit point of sequence an. Okay, so in the first case our result is proved. We have to show that the given sequence has at least one limit point. Okay, now second case is when then set S is infinite. Case second, S is infinite. Okay, S means range of the given sequence an. Since an is bounded, therefore its range means S is also bounded. Here S is range means set, so y the y Bolzano Weierstrass theorem for set. Okay, in the first unit we have proved that every infinite bounded set has at least one limit point, and this theorem is known as Bolzano Weierstrass theorem for set. And we are proving that every infinite bounded sequence has at least one limit point. So here we suppose that S is infinite and given sequence is bounded. Since S is the range of the bounded sequence, therefore S is also bounded. So S is actually infinite and bounded. So why the Bolzano Weierstrass theorem for the set S has at least one limit point. Clear? Say it is L dash. Okay, L is or we can write this like that, suppose limit point L dash. This is the limit point of the range. Okay, Now we show that the this limit point is also limit point of the given sequence. By definition, for H epsilon positive, H epsilon positive, L dash minus epsilon, L dash plus epsilon. For H epsilon positive, the neighborhood of L dash, this is the neighborhood of L dash, contains infinitely many members of S, because L dash is the limit point of S and S is the range of the given sequence. Okay, this neighborhood contains infinitely many members of S. Okay, and S is the range of the given sequence an. Clear? What every member of range S is also member of sequence an. Clear? Actually, a range contains all distinct elements of the sequence. So it's clear that every member of the range is also member of the sequence. So this neighborhood of L dash contains infinitely member of S and every member of S is also member of the sequence an. Therefore, the neighborhood of L dash minus epsilon, L dash plus epsilon. Okay, the neighborhood of L dash contains infinitely many member of an. This is hold for H epsilon positive. This is hold for H epsilon positive. This implies that every neighborhood of L dash contains infinitely member of the sequence an. This implies that L dash is limit point of sequence an. Okay, so here we have shown that in every case, if range is finite or infinite, every bounded sequence has at least one limit point. Okay, what about the converse of this theorem? Converse means if a sequence has a limit point, then it is necessary or not that sequence is bounded. So answer is no. A remark: the converse of Bolzano Weierstrass theorem is not true in general. Okay, here actually we have to construct sequence which has a limit point but not bounded. Okay, example, so you can construct many sequence which are not bounded but has a limit point. This sequence is like that: a sequence where nth term is, this is 1 when n is odd, and this is n when n is even. So sequence here is n is odd is term is 1, even number, 3 is odd, 4 even, 5 odd, 1, and so on. This sequence is sequence we can write here. Okay, actually this sequence is not bounded because we have terms 4, 2, 4, 6, 8, 10 and so on, but here 1 is repeated here infinitely times, so 1 is limit point. Here 1 is limit point of an what an is unbounded. Clear? So converse is not true in general. In the next lecture, actually we will define the Cauchy sequence and what is the Cauchy general principle for the convergence of sequence. Okay, thank you.